Hey everyone, it's Mr. Brandrick ready for our discussion about probability models, coming at you from H-Town 101, Christopher Jesuit. Let's do this. All right. Again, if you would like to read more about this is chapter 17 at the top of your paper. Chapter 17 from the textbook. It's online if you'd like to take a look at some of these concepts in a more chapter textbook written form. Okay? So, let's talk about our main man, Joseph Bernoulli. I put his photo up there in the corner. You should see it. It's really small on yours, but you can kind of see it on mine. So, the way that statisticians think about Bernoulli is he's kind of like the founder of the idea of probability. Okay? So, when we talk today about Bernoulli trials, that name comes from this man, Joseph Bernoulli. And I want you to notice that you're writing down 3 things that make it a Bernoulli trial. So there must, first off, only be 2 outcomes. Something that we deem success and something that we deem a failure. So when I think about the grades you could get in a class, what are the grades you could get in a class at Christopher Jesuit? A, B, C, D, F. Is that only 2 outcomes? No. Are there any classes out there, I don't know this, maybe you guys know this, are there any classes out there that are pass and fail? Would that be okay for 2 possible outcomes? Yes, you see the difference. Okay, so we must have only 2 outcomes. One we're going to call success, and one we're going to call a failure. The probability of success must be constant. What I mean by that is after we do an event, the next event we do should have the same likelihood of getting that success and that failure. Okay, and finally, we're hoping that the trials are independent. Whenever I read these, my first thought goes to what example of a Bernoulli trial? And we've done it in this class. What is an example of a Bernoulli trial that you have done in this class? Very good. Okay. Flipping a coin is an example of a Bernoulli trial. We have success and failure. Which one did we say was our success when we did it in the first semester? It was heads. That's what I cared about. That was our success. So failure is tails. Do we have a constant probability of success? Yes. What was our likelihood of flipping and getting a heads? 50% every time. Were the trials independent? Yes, they were, right? If you flipped a heads, is that going to affect the next flip? No. So a coin flip is the simplest way to satisfy this idea of a Bernoulli trial. Everybody good on Bernoulli trials? Okay? Now, I'm sorry, this word is all funky. Where'd that come from? Do you guys have that? Did I mess up? No? Okay, so it's just me. I did that? All right. Where did you come from? Well, now I'm just writing all over. Okay. The first model we're going to talk about is the geometric probability model. I want you to write next to this, in parentheses, I want you to write weighting. So whenever I ask you, because I'm going to ask you today, what type of model are we going to use? The question I want you to ask yourself, is this asking us to weight? Okay? I'll clarify more of that as we go further. But the idea here is that we are saying, what's the likelihood that we get our first success on the 6th try? So I'd be waiting until the 6th try to get your first success. So that's a geometric probability model. So we use geometric. Okay? Now, with that comes a lot of stuff. Now, what's nice is that in our use of these models this week, a lot of the notation is going to be the same. But there's little slight differences that can confuse students, so I want you to really start paying attention. First off, P and Q will never be changed. P is the probability of success, and Q is the probability of failure, or 1 minus P. All right, so P, probability of success, Q, probability of failure. Now with our coin flip, P and Q are the same. 50-50. That may not always be the case. Now, you should see this capital X here. You guys see that capital X? What is that called? From our Kahoot, what's that capital X called? A random variable. So we're saying that this random variable X, whatever we're deeming it for our context of our problem, is going to be equal to some smaller value X that will be a number. All right, if you think back to the example I just gave, if I said the first success is on the 6th try, this little x will become a 6. Okay? So we're waiting until the 6th try to get our first success. Now there's some formulas there in red. You do not need to memorize those. You will be given those formulas in red. All right? We'll be using those for the expected value or mean and the standard deviation. Now, you'll see at the bottom of this slide it talks about independence. Not always are we going to have any type of event that are independent each time. With coin flips, it's very easy. Okay, coin flips are independent events. But there will be times where you're like, wait, hold on, that's not actually independent. The example we do today, not independent. But we're okay as long as we don't violate this last thing down here. I feel like something, maybe if I do it this way? No, that didn't help. All right. If we don't violate this last thing down here, which says that the sample is smaller than 10% of the population. So we're going to check a condition today called the 10% condition. And as long as our sample is less than 10% of all the entire population that we could think of, then we're okay to move forward. We've actually talked about this before. All right? We've actually discussed this before in the first semester. So this is actually not something new, but I want to just mention it because it will come up in our example shortly. Questions about the geometric model? The geometric model. We're going to use it today. Okay. Now, the next model we're going to use is called the binomial model. I want you to write in parentheses next to it. I want you to write number of successes. Okay? So whenever you read a problem and it says, what's the likelihood that you get 4 out of 7 to be successes? That's an example of using a binomial model. All right? So weighting. So what's the likelihood that your first success comes on the 4th try? That's geometric. What's the likelihood that I get 3 successes out of 8 tries? That's binomial. All right, so the phrasing is different, and it will tell us what model to use. Now, I told you guys, some of the stuff's going to be the same. P and Q is still here. That's no different. P, the probability of success. Q, probability of failure. But we have some new stuff here. We have a number of trials for n, which we didn't have before. And now when we do this, we have a new thing here. It's called n choose x. Does anyone remember what that was? Oh, bonus points if you remember it. Not really. Do you remember what this is?
Oh, that's combination.
What is it? Somebody said? It's a combination. Nice job, Juliana. Remember when we did combinations and permutations in the first semester? Oh my gosh, it's coming back. I'm so excited. Okay, so we'll talk about how we're going to do that. And again, the stuff in red and in orange, you're not going to need to memorize. But we're going to use that today. Now, one more thing before we get into our actual problem. What's interesting about the binomial model is that if you get large enough successes and failures, you can actually start to see that the binomial model becomes the original model we ever discussed. Do you remember what it was? The first model we ever talked about? The normal model. Nice job, Yasmin. The normal model. So what's crazy is that if we get large enough, we can actually just say, we're good. Let's look at the normal model. Okay? And the normal model is the easiest one out there. Not the easiest. It's the most familiar one. It's the one that we work with the most. We're going to continue to work with the most the rest of the semester. So anytime we can use the normal model, it's a great idea to use it because not just you guys are more familiar with it, people that read your work are more familiar with it. All right? If you were to talk to the teachers at the school, all right, they're more familiar with that model. That's the most familiar they would be with. Even if they don't know the name, if you drew that bell curve, they would, oh yeah, I know what that is. Okay? So that's why we try to use it as much as possible. So if we have 10 or more, when we look at the number of trials times our probability of success, the number of trials times our probability of failure. So really, if we have more than 10 or 10 or more successes and failures, then we can actually use the normal model to approximate using binomial probabilities. All right, so you'll notice the very last slide on your notes on this first page, it kind of summarizes the 3 different models we're going to use this week. So I want you to put a star next to that very last slide on the first page, slide number 6, after you write this down. Put a star next to that last slide, because that's where you can kind of find a summary of the 3 models that you need to be familiar with before we take our test next week. Any questions about any of this so far? Again, the plan is to do an example in class here before we leave today. Tomorrow you'll get to work a lot of this on your own. We're actually going to work at our spots, all right, at the whiteboards and windows tomorrow. All right, so we do some of this, and then Thursday we'll do some group work with each other to kind of make sure we can ask each other questions if we're still confused. There's no quiz over this chapter. No quiz. Okay, so here's that last slide that you put a star next to. These are the 3 different models that I care about for this week. Any questions? No questions? All right, make sure you have a calculator with you. Make sure you still have your piece of paper there, your pen or pencil. Flip it over. Let's do one together. Peter, would you mind reading this for me?
A new cells gimmick has 30% of the M&Ms covered with speckles. These ruby candies are mixed randomly with the normal candies as they are put into the bags of distribution and sale. You buy a bag and remove candies one at a time looking for the speckles.
Thank you, Peter. Now, when I first made this problem 7 years ago, there were only like 3 different flavors of M&Ms. Now, if you go buy M&Ms, there's like, 8 of them? It's crazy. So I'm expecting at some point to walk down the aisle at Kroger and there to be a groovy M&Ms, even though I just made this up. I thought it was silly, but it's coming. Okay. The first thing I want you to do on this slide is I want you to ask yourself, is what Peter just read for us an example of what we would call Bernoulli trials? So I'm going to write down Bernoulli. Bernoulli? Question mark? What do we think? Is this an example of Bernoulli trials? Well, let's go down the checklist. What's the first thing that we know about Bernoulli trials? There are 2 possible outcomes. So when I reach into the bag and pull out an M&M, what are the 2 outcomes? Regular or groovy, speckled, okay? So does that check off that idea of 2 outcomes? Yes. So number 1, success/failure. We would write that is groovy and regular. Now, for our purposes, we're going to use groovy or speckled as a success. I'll repeat that out loud so you guys heard what I said. We're going to use a groovy M&M, or speckled, right, same thing, as a success. So what's the second thing we have to check for? What's the second thing we must check for with Bernoulli trials? Constant probability of success, or a constant letter P. What is our probability of success? 30%. Is that going to change when I pull one out and look at it? Now the answer is yes. Because there are a finite number of M&Ms that are made, right? Whether that's millions, hundreds of millions, I don't know, right? I don't make M&Ms. But there is a number. It's not infinite. So when I take out one, will that change the other probabilities? It will, but how much is it going to change? A very tiny amount. So if it changes a very tiny amount, we're still okay saying, okay, our P is going to be what? What's our probability of getting a success here? Of getting a groovy or speckled M&M? 30%. So I'm going to write P equals 0.3. What's the third thing? Independence. Independent trials or events. Now, independent means that if I pull out an M&M and see a groovy one or see a regular one, that is not going to affect the likelihood of me pulling out a groovy one or a regular one on the next try. And what did we just say? It will, right? It will. But there's a caveat here, and it's that condition I want you to write down. There's a caveat that allows us to keep going even though we're violating this idea of independence, and that's the 10% condition. Now, it's talking about opening up a bag of M&Ms. What kind of bag are you imagining when you imagine a bag of M&Ms? Like small ones, like snack size? Like a little, the little bit bigger, but the ones you get like when you're like almost checking out at Kroger or H-E-B that are on, okay? Those like big, they're like personal size, right? You know, and we're done. Yeah. One serving. Yeah, sadly, I bet that doesn't even say one serving on there. Sad. But yeah, I would agree. That's like half a serving, okay? So that's not many, right? Maybe, 40 M&Ms? Not a lot, 50 M&Ms? How many M&Ms do you think are made in the world? A lot? Millions?
Like more than like billions.
Let me ask you this. If we think we have 50 M&Ms, what's 50 times 10? 500. Do you think that they make more than 500? So we are good to keep going because our sample size, our 50 M&Ms, is smaller than 10% of all the M&Ms that are made. All right, so that is just a process I want you to start getting used to. You're going to do that a lot over this semester, okay, until May, where we have to think, are we going to be violating that? Okay, yes we are, but does this condition allow us to keep going? All right, and it does. So we're good. Bernoulli, yes! Let's do it. What is the probability that the first speckled one we see is the fourth candy? So I pull one out, not speckled, sad. I pull another one out, regular, not speckled, sad. I pull another one out, not speckled, sad. The fourth one, groovy. Now, what kind of model is that? What kind of model is that? What kind of model is that? Are we waiting to get our first success? Or am I asking you to find the likelihood of a certain number of successes out of a certain number of trials? We're waiting. So this is going to be geometric. We are waiting to find our first success. All right, so I'm going to write for the probability of our random variable, which is capital X, equals small x. But what is that small x going to become? Very good, Yasmin. It becomes a 4, the fourth one. All right, so you just told me how many in a row do I get that are regular? 3. So what's the likelihood that I get a failure, which is a regular one? Because we know the probability of success is 0.3, right? So what is the probability of failure, or Q? 0.7. Very good. So I'm going to write 0.7 times 0.7 times 0.7. You see how that's 3 failures in a row? Regular, regular, regular. And then what's the fourth one? 0.3. Groovy. Take out that calculator to tell us what this is. Take out the calculator. Tell us what 0.7 times 0.7 times 0.7 times 0.3 is. Sabrina got 0.1029. Yes, we agree? Thanks, Sabrina. 0.10. I'll just go and round to 3. 0.103. So we have a 10% chance that the fourth M&M will be our first groovy one. Questions on answering that? Please ask now if you're confused about where we got any of these numbers. The next one. What's the probability that the first speckled one is the 10th one? Now what model am I asking you to use? Would it be normal? The only way to get to normal is to go to binomial first. Right now I'm asking, is this geometric or binomial? All right, I got you guys. It's still geometric. Am I saying what's the likelihood that I get 4 speckled ones out of 8 total? No, I'm asking, we're waiting until which one to get our first speckled one? The 10th one. We're still waiting. All right, so this is still geometric again. But now the probability of our capital X, our random variable, is going to equal 10. Now to make this look a little nicer, I'm not going to write 0.7 times 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 0.7. Not yet. We're getting there, but I know you want it. I love factorials. I'm going to write, I'm not going to write that. First time, I know, I'm sorry. Just lost 3 subscribers. 0.7 to the 9th power. Why did I put 9? Because what happens on the 10th one? I get the groovy one. So what is 0.7 to the 9th power? Woof! Times 0.3. 0.012 is what I heard. Confirmed, anyone? Yes? So is that very likely? That's 1% chance that we'll get it on the 10th one. Not very likely. Now, it says to write a general formula. We don't need to do that. We have it. Go ahead right now and flip to the front page. And I want you to take a look at this slide right here. So we changed this little x to be what? 10. And so this is Q. What's Q in our problem? 0.7, the probability of a failure, 0.7, to the 10 minus 1 power. What's 10 minus 1? Did we raise it to the 9th power? We did. And then we multiplied times our P, probability of success. So we use that formula without even talking about it. Everybody good? Okay, let's keep going. Flip back to the problem we're doing. Ooh, I like this problem a lot. What is the probability that the first speckled one is one of the first 3 we look at? Now, I don't really want to ask you about what model we're going to use. I just want to think about this. It's one of the first 3 we look at. So what's an example of how we could find a speckled one that's one of the first 3? I pick out an M&M, and what is it? What is it? It's groovy, it's speckled. Great. So that would mean 0.7 and I'm done. I lied. 0.3 and I'm done. I picked it up and it's Groovy. Done. Because I want one speckled is one of the first three we look at. Plus, what if I pick up the first one and it's not groovy? That's 0.7. But then I pick up the second one and it's groovy. Done. What's the last way of doing this? I pick up the first one. It's not groovy. The second one? It's not groovy. The third one? It's groovy. So it'd be like that. So what is all that added together? .657? Yeah, confirm. Now, the reason I threw this problem in here is because what if instead of saying it's one of the first three we look at, I said it's one of the first 25 we look at? What's going to happen to this problem? It's going to be super long. All right, so I want to show you tomorrow using the computers how to do this. All right, because when it's really short like this, we can do it with our calculators. It's no problem. But tomorrow, I'm going to ask you a question that's going to be a lot more challenging, a lot longer. So I want to show you tomorrow on the computers. All right, you'll get to use the computers on Thursday as well. How many do we expect to have to check on average to find a speckled one? So if I'm opening up my bag of M&Ms and I ask myself, I wonder when I'm going to see that first speckled one, this question will help me gauge of when I should expect it. All right, so the first thing I see is expect, and then average. What are they asking you to find? They're asking you to find something. Expect or average. They're asking you to find the expected value or the mean, mu. Okay? Now there's a formula we have on the first page that says, if you look at the third slide, the expected value for the geometric model is 1 over P. Well, what is our probability of success? 30%. Very good. So what is 1 over 0.3? 3.3 repeating? So it means when I open up my bag of M&Ms and start picking them out to eat them, when am I expecting to see my first groovy one? Between the third and the fourth one. I can't have, right? I can't have half an M&M. So I'm expecting to be the third or the fourth one. Will it always be that way? Could it be the first one? Absolutely. Could it be the eighth one? Of course. But as I open more and more bags of M&Ms and figure out when I'm going to get the first one, taking the average of all those, it's going to give me around 3.3. All right? That's what expected value means. Let's do one more. What's the probability that we'll find 2 speckled ones in a handful of 5 candies? What model am I asking you here? I'm asking you number of successes, so this is called a binomial model. All right, now this one is a lot of fun. I hope you guys enjoy this. X is equal to how many successes? 2. Now watch this. What's our probability of success? 0.3. How many do I have that are successes? 2 of them, right? 2 speckled ones. How many failures do I have then out of 5 total candies? 3. So a lot of students do this, and they tell me this is the answer. What is 0.3 squared times 0.7 cubed? Let's see. 0.3 squared times 0.7 cubed. 0.031. Why is that not the answer? What is this saying? This is saying the first two that I get are what? Are speckled. But does it tell me that the first two have to be speckled? Could they be the last two? Could it be the first and the fifth? Could it be the second and the third? See where I'm going with this? So we have to ask ourselves, how many ways can we have 5 candies and choose 2 to be speckled? And oh my goodness, this is called a combination. Okay? So we have 5 total candies and we're choosing 2. So the formula for this is n factorial over k factorial times n minus k factorial. So that's 5 factorial over 2 factorial. What's 5 minus 2? Times 3 factorial. Now you can do all this math, because what is 5 factorial? 5 times 4 times 3 times 2 times 1, 3 factorial, 3 times 2 times 1. Or, what can you do in the calculator? Hit the number 5, and then hit, yes, Sylvester, PRB. And which one do I want? I want combination, because does the order matter? Do I care if it's the first 2 or the last 2 or the middle 2? No, combination order doesn't matter, so hit 2. And then choose 2, so you have 5 NCR 2. And it tells us how many different ways? 10 ways. So you take that point 03087 and you multiply it by 10. So that becomes a 10. So what is 0.031 times 10? It's going to be 0.309. So we have about a 31% chance of getting 2 speckled ones and a handful of 5 candies. All right, that's it for me. Thanks for listening. Thanks for watching. Like, subscribe, comment, and I'll see everyone tomorrow.